third and final lecture on interaction effects in graphene. And today we will move on to talk about hydrodynamics, or in other words, DC transport. And also I will discuss some aspects and implications for ultra-fast optics in the system. As I mentioned earlier, the first part, and also what I discussed last lecture, was primarily done in collaboration with Dan Shi at LSU. The hydrodynamics calculation with Lars Fritz, Markus Miller, and Suki Sachdev, and the fast optics work with Jigang Wang and Junho Zhang. Junho is a student, or used to be a student of mine, and Jigang is faculty at Iowa State, doing ultra-fast optics. We have seen this, the implications that we have a Dirac spectrum, and that we can, for example, as function of carrier density that can be gate controlled and temperature, and those are actual units for those systems, find different regimes, namely when we are close to this Dirac point and raise temperature, then even down to lowest temperatures, the system will be governed by this linear spectrum and the Dirac cone, and get, for example, heat capacities, compressibilities, and other experimental observables that have log corrections to Coulomb corrections that have been measured in a number of experiments. Now we can also go to more high density and low temperature regime, and then we have the whole electron semi-liquid, so that we crossover behavior separating those distinct regimes, which is the reason why, in fact, the notion of quantum criticality is very powerful to characterize the physics of the system. I already discussed that we wish to look into the DC conductivity and the shear viscosity. The latter is the relaxation of a gradient in the velocity field, and we can see how momentum is being transferred transversely, for example, to a velocity gradient. And so this is the energy momentum tensor, or the momentum flux tensor. So where momentum moves, changes in the y direction, the x component of the momentum changes along the y direction, for example, as a consequence of the velocity field gradient. And the corresponding transport coefficient, again, is the shear viscosity. So those two observables have, just like densities, scaling dimensions, and therefore we can use scaling principle to calculate them. Let me once repeat the notion. We're in D equals 2, so that's just of coefficient 1. What we want to calculate is the conductivity at the physical actual frequency or temperature and coupling constant. That's a hard calculation to do, and therefore instead we use the fact that the coupling constant during the flow gets smaller, the temperature and frequencies get larger, and therefore we need to solve the high temperature, high frequency, depending which limit we wish to take, but small coupling constant regime that we can solve alternatively, and then just use scaling arguments to obtain the proper logarithms. And I also mentioned that if you want to have the shear viscosity, then the entropy density is a natural way to normalize it to get some effective, because they carry the same scaling dimension. And finally, I also stressed that will become a little bit later when we talk about fast optics. The transmission coefficient is determined essentially if we ignore correlation effects, which in this case we can because of very small coefficients, as we discussed, is ultimately determined just by the fine structure constant, and we have a 97.7 transmission through a single sheet of graphene. The rest is being absorbed. Good. Now, we saw that the AC finite frequency conductivity, again, is a constant. At finite temperatures, there's a region of order kT, where we're suppressing it, build a Drude weight, and this is what we discussed last time. Now, and we went through all of this. The regime that we wish to discuss now is what happens to this Drude weight here. So again, we have a coefficient, a Drude weight, at the neutrality point that is exclusively given by thermally excited carriers. If you're going to finite carriers, then, of course, the Drude weight is given by those carriers. And then you need to do plasma physics to see how correlation affects the Drude weight. Here we have exclusively thermal excitation. That's why there's a T here and some trivial numbers. Now, let's guess the answer. What happens when you take into account collisions? Really, what we would all expect is that the delta function becomes a Lorentzian and is governed by some scattering time. This will, of course, be a transport scattering time. Now, at zero frequency, so the AC conductivity will just be omega goes to 0, so therefore we get nothing else but a tau here, tau over pi. And correspondingly, the DC conductivity taking this result will just be given by some k Boltzmann over some rate. And there will just be E squared over h up front. Because this will be ultimately the result of the DC conductivity of that system. Now we can even use scaling to go a little bit further and argue in the following way. Oops. It used to look right. Well, I'm going to finish this off eventually. So we're looking for tau to the minus 1 right in each bar. That's an energy. It's a critical system where exactly the neutrality point. There's really only one other energy we can come up with, which is k Boltzmann T at this point. So when whatever calculation we do, we'll get its dimension from k Boltzmann T because it's a quantum critical system. In addition, we can see, well, since we are allowed to do perturbation theory, that's what we discussed, right? The scaling goes to smaller and smaller coupling constant. So in that regime, we can do perturbation theory. The linear order in the fine structure constant we've analyzed in great detail gives us logarithmic velocity renormalization. But that does not imply any scattering events. There's no lifetime associated. It's still a perfectly infinite lifetime, it's just a velocity that's been enhanced. The leading lifetime correction comes only at quadratic order in the dimensionless coupling constant that we have. Right? It's dimensionless because we already fixed units here. Therefore, this can only be our fine structure constant, and then there will be some number up front. So therefore, we know what's the result already, and this must be ultimately the result, because we can do perturbation theory. There's one caveat to that problem that we will get into. If this is the right result, I can insert a k Boltzmann h bar t to the minus 1 here, and the k Boltzmann t here that comes from the number of thermally excited states is being cancelled by the k Boltzmann t that comes just from the fact that there cannot be any other scale but k Boltzmann t. Good.
How can you say about the exponent?
Which exponent? This exponent?
The temperature.
That's just, at the moment I'm just guessing the answer. And I say, well, I just take what I get for a non-interacting electron gas. So therefore, that's a straightforward calculation. I just have the number of errors is just linear in T. The number of thermally excited, the Drude weight is just given in T. That's just a free particle calculation. That's where this one comes from. And then I just guess what the answer here would be. I'm going to do a horribly complicated, detailed transport calculation in what follows. I first wanted to motivate it. So therefore, this is just the power is given by free particle physics. This power is given by dimensional argument. This power is given simply by knowing that the leading order doesn't give anything. So the next best is to take the quadratic order. So therefore, I can insert this here, and I find ultimately that the DC conductivity is E squared over H, some other number, which is just my log 2s and so forth, my 4, and that number here together. Then I have k Boltzmann over T cancels, and all I have is 1 over alpha squared here. Right? So now, this is the perturbative result. Now all we need to do is to use our scaling arguments. In other words, that alpha is being replaced by 4 divided by log omega, log T. What we therefore find is we will expect that the DC conductivity will be E squared over H times log squared T. In other words, simple scaling arguments enforce us that simply because we know how the coupling constant goes, that the coupling constant is a running coupling constant, that the DC conductivity at low temperatures will have to diverge. But very, very slowly so, only logarithmically. So the resistivity goes to 0, but only like 1 over log T squared. Good. In that sense, graphene is a metal. Perfectly clean graphene at the neutrality point when you cool down. Impurities will spoil all of that. So this will be cut off at some finite temperature. But here is to do a calculation that is true even next year, and at some point parameters will be good enough to measure that. So far, that has not been measured.
So,
yeah.
So this 4 is because of the evidence, right?
Which, oh, this is just from our RG. Ignore it because it's going to be. There's no. We had a flow equation that had a flow somewhere.
But before we go into conversion, can I ask you? So there are are there any value transitions which you have to take into account? I mean, so far it was like single development collision, so you have just one direct code.
No, we have 4 direct codes.
Well, correct, 4, but I mean.
No, that's not this 4 here, but never mind.
But there are never any matrix elements which you have to compute so that which were scatter relations.
Oh yes, sure. This calculation here is a calculation of scattering processes, of course. That was the first and the second lecture, where we had to calculate surf energies and see how coupling constants are renormalizing.
No, so there are interval scattering.
There is no intervallary scattering because Coulomb interaction is important at small momentum. Yeah.
Good question. And so the fact that it's perturbative also tells you that I can't, the high energy cutoff cannot come in the calculation for 1/tau, and therefore I can't construct some other funny energy scale, right? Because lambda shows up in alpha but nowhere else. The
Right.
cutoff, right?
Yeah.
And that's not.
Yeah. But also, I mean, in the end, you need to do an honest calculation, which is what we want to do next. How would you do that? Since we have a leading order in the fine structure constant quasi-particles that have a renormalized velocity, we can do Boltzmann theory because these are well-defined particles still. These don't have strong, lifetime effects with enormous powers. Therefore, all what we need to do is to calculate the Boltzmann, solve the Boltzmann equation. Boltzmann equation, we just have some driving term here, which is given essentially by the electric field. We will go into a stationary limit. This is important. There will be a collision term that it takes into account the next order corrections. And for critical system, actually for the superconductor insulator phase transition, this was done by Damley and Suchdev long ago, and we just need to use their insights in order to solve it for this system here. We have a distribution function which we can expand in the electric field, where we say, well, that will be our Fermi function, and then an appropriately defined, this is just F1 minus F for convenience, distribution function which we call chi. All the physics, the non-trivial physics, is encoded, of course, in this part of the distribution function. Once we know it, we know the conductivity. Because everything can be obtained from the distribution function. It's linear if it's linear in the lights. Good. Now, this collision term is a bit of a pain to calculate because we got all kinds of transitions. Yes?
Do you still need the lights?
Absolutely.
Thank you.
Thank you. So this collision term, I only bring this, show it here to you to realize that it's a bit of a pain, and to get this, basically what we are doing here, we're trying to calculate this number. To come to this logic here, it takes about one afternoon sitting in Aspen on the lawn. To calculate the number takes the next half year. That is up front there. But what can you do? So you need to look at all those diagrams and analyze them, and in the end find a solution of the Boltzmann equation. But see, it's a linear integral equation, which makes it a bit complicated because we have the distribution function everywhere here in the collision integral, and we also have it here. Usually you do a so-called relaxation time approximation, but there's no reason that this is any good. So we need to actually solve that integral equation. And the way you do this is formally in the following way, that you say, well, the left-hand side is some operator. The collision operator is also an operator that acts onto our function chi, and what we really need to do, we need to invert that operator. You can introduce scalar products and an inversion of operators and use lots of the intuition that we have from quantum mechanics to then solve the conductivity for this problem, where we just need to, well, basically invert the collision operator, which you can see here, right? If this is the Boltzmann equation, well, that's the solution. Well, for that, we need to have a space of eigenfunction of the collision operator, and that's why it makes sense to think about those a little bit more. But before we go there, I need to show you there's something very interesting about graphene. You already see this when you look at the Fermi's golden rule, where we have two particles coming in, scattering into two other particles, and this is here the Coulomb matrix element between initial and final states. In graphene, we have an energy conservation here, and of course momentum conservation. Momentum conservation has been included already by just having three independent momenta, k, k prime, and a transfer momentum q. Energy conservation is this equation, and what I call S as prime, R, and R prime are either plus or minus 1 because the energy is either in the upper cone or in the lower cone. And we need to go to all 16 combinations to see which processes are allowed. If I have two states that are in the upper cone, plus plus, there cannot be two final states in the lower cone and conserve energy, right? Because both initial states are positive and final states are negative, and they can't be equal. So therefore, those two are immediately not allowed. But we are lucky. There are another 8 that are also not allowed, where we have, say, 2 from the upper and 1 from the lower, and others. Why is that so? Because this here, since we have a linear spectrum, those are just the lengths of 3 vectors. And if we draw that, it turns out. Sorry about that. There's a simple rule in mathematics, which I discussed this morning with my son, that if you have a triangle, it turns out that one side, even the longest, is always shorter than the sum of these 3 others. Right? Good. This rule. Therefore, if you go through this, those are just the lengths of 4 vectors that close, right? Because of momentum conservation. And because of this, those 8 processes are all not allowed. Because you cannot fulfill energy conservation. There's only one exception, namely when all 4 vectors are pointing in the same direction. That is so-called collinear scattering. That is the only one that has a larger phase space. What we are left with are those transitions here, and they are interesting because we have 2 states that are initially in the upper one that scatter into 2 other states in the upper or lower. Or we have 1 in the upper and 1 in the lower. There's interband scattering, going into 1 in the upper and 1 in the lower, or vice versa. But what we do in all those processes that are allowed is that we conserve the number of holes and electrons individually. We never have a process where during the scattering process we are enhancing the number of holes or electrons. That has an implication, namely, if you have a non-equilibrium distribution function, then it is very hard for Coulomb interaction to relax that distribution function by changing the total number of holes and electrons. So therefore we have a pseudo-conservation law, because higher order processes will spoil this effect, but they are always weaker in their effect, that we have a conservation of electrons and holes individually in scattering process in leading order and Coulomb interaction.
Can I ask a quick question? Sorry to interrupt you. So do you need to, did you include the pseudo spin as well? Because that will give some more selection rule. For
no, you don't,
scattering.
because the Coulomb interaction will not allow you to scatter between different values.
So it won't matter.
No, it won't matter. Good. So now we have some ideas that when we want to invert an operator, it is very important to know about conservation laws, because any conserved quantity gives rise to a 0 mode of the collision operator. And then you will think, I can never invert that beast if there are 0 modes. But of course, that's been known for a long time. If the driving term is orthogonal to the 0 mode, we can orthogonalize it in the subspace that is orthogonal to the 0 modes. There's a famous example we discussed yesterday. A p-squared dispersion relation, a non-relativistic dispersion relation, has a 0 mode. That 0 mode is momentum conservation. It's just a certain wave function of the collision operator that doesn't change. It's a 0 mode of the collision operator. The driving term for this problem is, however, not orthogonal to the 0 mode, and that's why we have infinite conductivity. The inverse of the collision operator is infinite. That's why the free electron gas has an infinite conductivity if we don't have impurities in the system. If you have impurities in the system, momentum conservation is violated, and that's not any longer a zero mode, because there's no conservation anymore. Good. So, but in our case, we are lucky that all conserved quantities are orthogonal to our zero modes, which we of course have energy conservation and so forth. But we also have another zero mode now, which is our particle pole conservation at that order in the calculation. It's going to be better soon, we're almost over. So there's only one caveat, namely these collinear scatterings. And it turns out they are dominating the transport. They get additional logarithmic divergences.
So you're saying that you're saying that you have orthogonal to zero modes because you couple to the difference between particle poles?
Well, yes, exactly. So, because the electrons move in this way and it holds in that direction. If an electric field would move both in the same direction, then it would not be a problem. So now we know that our collision operator has those funny collinear terms that have more states allowed and collinear terms and non-collinear terms. They are the dominating ones. So it would be natural to say, well, let's just confine ourselves to this subspace. If we do that, we find that in this subspace, it turns out that this is the zero mode and it's actually not orthogonal to the driving term. That would mean if you were to only look at the dominant scattering processes, they're so dominant they would give us an infinite conductivity. Funny enough. But we know, therefore, we can take advantage of this. We know some eigenvalues and can therefore invert that problem exactly. There are now a couple of technical steps. But using all those logics of dominant collinear scattering processes and the emergence of a new zero mode is a problem that is related to the particle hole conservation, we can actually invert this in the subspace of those functions. And then you can indeed get the matrix elements calculated. We know the zero mode, we know the driving term, and we can calculate our coefficient. The number is 0.760. And otherwise exactly as expected, e squared over h and r squared. Everything follows indeed as expected from this transport calculation. So therefore, we know that the conductivity, we go on, indeed goes like the logarithm of the temperature if you use the scaling arguments. And this curve has no free parameter except for the upper cutoff of the Dirac spectrum. So this height here is a non-negotiable one in this system. Good. Maybe I move on here because otherwise we'll never get. If we can do the same calculation to do shear viscosity, where we have velocity gradients in the system, and where we have no tensorial driving terms. And again, I motivated this last lecture. Here, you can find that there are actually two zero modes, and you can, again, invert the problem, you can find, again, a universal answer for the shear viscosity of that problem, which is 0.449 times what you would expect by pure dimensional reasoning. So, this is an interesting result, because now we can use our earlier calculation of the heat capacity, which gives us the entropy, to calculate eta over S. And again, the supersymmetric anti-de Sitter conformal field theory analogy gave an upper limit for eta over S for all reasonable systems except for multi-component classical systems. And so we have our result for the heat capacity, which is our earlier heat capacity result, just integrated appropriately. We have the just determined shear viscosity, and it turns out because these two zero modes conspire in a very destructive way that we find a very, very small coefficient of a diverging log squared term of the shear viscosity. So therefore, we argued that graphene can be considered an almost perfect fluid with an exceptionally low viscosity, which is what you have in a strongly interacting system. Right? That's kind of counterintuitive because we think about viscosity mostly in the context of honey, where the viscosity is not determined by a Dirac spectrum, but by collisions of particles and interacting terms. Here we're in a very different regime, and it's the low viscosity that is the strongly interacting, just like the low conductivity is the strongly interacting system. Right? So that's what we argue the system is a perfect fluid, and then you can look at implication. You can obtain from the Boltzmann equation the corresponding hydrodynamics of fluid equation and Stokes equation. And essentially you have a nonlinear term here that gives rise to turbulence. And turbulence is typically being ruined by large by a large viscosity, because then you dampen the system efficiently, and you wouldn't get turbulence. But since we have a low viscosity, we can calculate what is called the Reynolds number. So basically, it's a typical scale to compare this number to that one. And so we argue that this system should undergo turbulence, which is important because when you want to have small contacts in graphene, you want to have a nanoelectronics device, you do want to know whether if you drive it with an electrical field, the electrons would undergo electronic turbulence. And we made this proposal here, and there was, well, recently a group at the ETH that does these numerical simulation of those Navier-Stokes equations professionally, and they did find indeed that here for Reynolds number 25, which is not very large, you would normally think that turbulence goes in two-dimensional system only for Reynolds numbers about 200. You already find large tendencies for turbulence. So therefore, when you have, for example, a little tip here that is kind of a confinement where the electron motion would go through, and you would immediately induce. This is just a function of time. Initially, you inject these particles, and then they integrate this as a function of time and found the evolution of turbulence in that system. So what you find is that the Coulomb interaction is so strongly correlated that it gives you a low viscosity, which drives the system into a turbulence state. Good. Now, at the end of this, I want to come to something that is also related to this pseudo-conservation law. Namely, we want to take graphene and inject a laser pulse. And we want actually to have the intensity of that laser pulse to be so high that we can get many states up here. Now, we know there are all kinds of collisions now taking place. These collisions to solve the corresponding equations give rise to what is essentially a quasi-thermal equilibrium state where you have hot electron temperature very often. Well, but here we have a somewhat different situation because once we switch off our pump proles, all those collisions can take place. But initially, at least, when the Coulomb interaction is the most dominant one, we have a conservation of those states up here and the holes that we have here that cannot relax by Coulomb interaction. That will stabilize a population inverted state. Right? So you can, and therefore the idea was, well, this should be observable in ultrafast optics. How would you do that? So the assumption is, well, this will essentially thermalize here, but we will do this at different chemical potentials because they just can't relax. If that is true, and then these are here pump probe experiments where indeed there's a pump hole, there's essentially relaxation due to phonons, and we're talking about this early relaxation, say in the regime of up to 100 femtoseconds. These are data from Jigang Wang and his students in Ames. So if we model, for example, this population inverted distribution function by nothing else but the hot electron temperature with an electron temperature and the chemical potential that can be different for the lower and the upper branch, simply because in this transient state we're in a non-equilibrium situation and we have different chemical potentials. You can just use either Celtic formalism or your own intuition to obtain what the optical conductivity of that problem is. And that's what the result is. It's basically our earlier result, just with now split two terms that has the two different chemical potentials with the appropriate signs. And there's something funny happening, of course, that at sufficiently low frequencies, the optical conductivity becomes negative. That's exactly what you expect when you have a gain medium, like in a lasing system, right? Where if you were to inject a beam, then you would have stimulated emission, right? Rather than an absorption. And the problem is therefore the conductivity changes sign. But the condition is exactly when these two chemical potentials are distinct below a certain frequency. So therefore, the electron temperature and the chemical potentials can be easily obtained from just simple conservation laws of particle number and energy. So the photon energy plus the initial energy should be the final energy, and the number of photoexcited states tells us by how much the upper and the lower branch rise. Simple argument. So then, and I'm almost done with that, then you can look at the change in the reflectivity, that's what the experimentalists do, with and without substrate plus graphene and substrate properly normalized. And simple electrodynamics tells you that this is related to just our conductivity. And we can do this, and it's only the real part, and because we can expand in the 1 over 137, right, which is a small number, and we know this is the leading contribution. If you then say, well, at some later time, and some initial time, the difference in the reflectivity, which is what's really measured, is then given by the change in the conductivity at some later time after the pulse and before. We know exactly what the conductivity before the pulse is. It was E squared over H, and the number from the new Coulomb corrections was small. So therefore, we can check when this here would be 0, we should reach a critical reflectivity, which you can obtain. And it's just given by the fine structure constant and the substrate's dielectric constant. Once the reflectivity reaches this value, the negative value, then we know that the conductivity must have been negative, 0. And here are the results, where you increase the pump frequency, and you do find indeed that you get beyond this value, which we then claim is a regime where the conductivity of the system is negative. Of course, what you really want to do is you want to probe this more directly. And therefore, you can do two things. You can actually obtain the conductivity in two regimes. Once, when you actually pump with a certain frequency, and then probe with a lower frequency. Then you should see the actual negative conductivity. And that's also been done, and you can indeed see that once you do the pump with a lower frequency than the probe with a lower frequency than the pump, that you then get into a regime where the conductivity is negative. So by that, we know that at least on a very short time scale, we can population invert graphene, and the origin, in my view, is that Coulomb direction is simply not capable of relaxing the thermally excited upper cone states, and we have this quasi-conservation of electron holes, and that makes the state rather long-lived. It can thermalize itself in some hot electron temperature, but more importantly, it has distinct chemical potentials. So I can conclude this, that some of the more sophisticated conclusion of what we discussed in the first two lectures, namely that there's a criticality in the system, and that Coulomb direction does play a role in graphene, has implications on the one hand in the hydrodynamic transport. We know it has a conductivity that will diverge like the logarithm of the temperature in a perfectly clean system. It will eventually cut off and probably go back to some universal value that's given by impurity schedule. And the second, that this Coulomb direction in the Dirac spectrum phase space gives rise to a pseudo-conservation law that at least at short times, and the leading terms in the directions are important, that gives rise to a population inversion, well, and maybe broadband lasing, and that's how you can build an ARPAS spectrometer where you can tune the laser frequency. Of course, only for very short time. Thank you so much for your attention.
I have a little question to that last part.
Yeah.
So I pump up, I shoot out the holes up to the upper band. And then you said later times I thermalize via lattice vibrations.
Oh no,
how do I thermalize at the beginning?
Maybe let me be more precise. Maybe it wasn't quite clear. The idea is you would excite some states, and they will initially actually undergo some kind of Rabi oscillations and will be a coherent system. But they will decohere, and that decoherence will be governed by the electron-electron interaction. And this gives rise to a population-inverted state where you have essentially a thermal distribution, which will never be quite thermal, but I think you can reasonably well characterize it as such, of electrons and of holes. Eventually then, this hot electron temperature will cool down and will relax towards the bath temperature by coupling to the thermals. Yeah. And so there are two thermalizations, one the real thermalization and the other one is kind of a pseudo-thermal distribution of the electron system as an isolated subsystem.
But then you shouldn't, like the laser energy shouldn't be too high. Or, I mean, if I... No, it should. Yeah, yeah.
Actually, because phonons are not very efficient here, right? I mean, what we solved actually all that problem and how this relaxation takes place from the phonon system, in particular this state here, an initial state, doesn't relax very quickly. Because acoustic phonons are not very powerful, and acoustic phonons you need quite a lot of them, particularly when you have high spectrum. Right?
Do you have the time scales from the experiment?
For the phonons?
No, for the parameterization.
Yeah, 40 to 80 femtoseconds.
Well,
Well, it seems that the pulse width is about 20 to 40 femtoseconds. And then we have no indication that it seems that after the pulse is over, they're already phonolized. In the core. Yeah.
Yes.
Yeah. Well, you started answering my question. Role of acoustics
Yeah.
to that derivation, to basically 1 tau.
Yes. Acoustic phonons are, of course, irrelevant in the renormalization group sense, so they will only give small corrections to this one.
Why?
That are negligible. Because their scattering is irrelevant compared to the Coulomb interaction, that's marginal. So you find, first of all, higher order in powers in temperature. It doesn't go, you get, here we have a conductivity or a scattering rate that goes like alpha squared T, and phonons give you a higher order power anyway. I think it is T to the 3 half. I have done it, but actually recently, but I forgot. It's definitely a higher power.
What about intercom? Intercom with the help of phonons between the K and K prime point.
Yeah, but for that, you can't do this with an acoustic phonon. Therefore, you need some large momentum transfer, and therefore not at low energy.
Phonons have large.
Right, but we're talking about low energy. At low energies, there's no phonon that can get you from one phonon to the other. Right? Eventually, of course, everything will be on by phonons. I would think so, but we're talking about the low energy physics.
So if your electrons thermalize on the time scale comparable to the pump,
Yes.
then what is the bump, the decay that runs from 250 femtoseconds?
Is it?
Yeah, no.
This is optic phonon, this is acoustic phonons, I think. That's roughly what's happening there.
So why are the acoustic phonons inefficient in this sense?
Oh, well, because they don't carry much energy. You need to, you're right. You need to.
No, I'm talking.
You need a lot of phonons to get this done.
Optical models for
So are the conversations from the from coupling?
Yes, they are.
Do we explain this?
Yeah, we have done this coupling.
Yeah.
You can understand that.
So what is the value compared to graphite? What's the value to the electron phone?
We took it from graphite.
So it's the same.
Yeah, it's the same. No, yeah.
Yes.
So today you are saying phonons are not important in low energy. But in your first lecture you said phonons gives low energy king. So which one is true?
No, I didn't say low energy, I said king.
So king is at what energy?
Well, it's higher than what we're talking about here. This is the beauty of this calculation is that you can go through it. You look at the leading terms at sufficiently low temperatures. I mean, the hydrodynamic calculation. We have two very different calculations here. The hydrodynamics calculation looks at long-range Coulomb interaction and looks at the leading low temperature behavior. And the phase space of scattering that you have at low energies due to Coulomb interaction is just much bigger, and you have much more important Coulomb interaction than electron interaction. They're irrelevant compared to those marginally irrelevant coupling constants. That's why the hydrodynamics is dominated by this. In this short-time dynamics, the phonons are very important at long times. But if we focus on short times, the interaction strength is just sufficiently small compared to the Coulomb interaction that we don't need to worry initially about. It's a very different reasons, in fact, why one is a scaling argument, the other one is a number argument of strength of coupling constants.
You have the reference to that data or just a name?
Submitted to Nature Physics, so far not shown to anybody else. Okay. No, Nature Photonics, yeah.
characteristics. This is not very practical question for such short time.
For
IV characteristics, something like S shape or N shape. As I said, maybe it's not very practical question for this short time, but in principle, something like S shape or N shape.
you can study, for example, what we did do is the implication of this population version, for example, on the low frequency Druder's behaviors, which gives you some information about what you want to do. You see changes, but I didn't see anything really exciting there. You just get an enhancement of the Druder. And therefore...
No, that's a different question.
Yeah.
But I mean something like the IDV, negative the IDV, like S shape or N shape IV characteristics.
Yeah.
In principle.
I personally think, if you, let's go back to this here. This is the AC conductivity. I think if you go back in the DC limit, this goes up. So therefore, I don't think we get negative DIDV or phase separation, whatever you could expect there. Yeah. No, I don't think you would get it. I know, yeah. You I think if we go to the DC limit, this will go up.
Jörg, you show us a really beautiful calculation for an idealized system.
Yes.
And you say, okay, I know. Well, first of all, you say this hasn't been; these effects haven't been seen yet.
Yes.
I know that that can be due to the fact that real systems have some disorder.
Yes.
But perhaps tomorrow, perhaps the next day, these systems will be clean enough to see these effects. This is a perfectly reasonable approach to most, as far as the hydrodynamics goes.
Yes.
But in a freestanding graphene system, there is, as I understand it, and I think you mentioned it at the beginning, intrinsic instability of the graphene sheet to dimpling.
Yes.
And this will always give you some background scattering from what amounts to disorder.
Yeah.
Have you estimated what that scattering rate is and how long you can
I
get?
haven't estimated this, but Oscar Buffett did. So therefore, if I just take his numbers, there's room of, what you need to see is, can I reach, if I were to increase my mean-free pass, so that it's clean enough, so that I can see this increase in the logarithmic value, the logarithmic increase of the conductivity. Then at some point I will be cut off either by impurities, or I will also might be cut off by wrinkling of the system. So if I take what Oscar and Eva Herbert have done for this value, there is the really dangerous thing to be still impurities and not the wrinkling transition. So basically one can make this very quantitative, because one just needs to go onto this curve and ask,
Yeah, exactly.
when do I stop?
Right.
Right? If I stop here, right,
You're
I
dead.
don't need to bother to try to fix this to a log square. Right? So in order to impurities to at least go, I think, to 0.5 something like here, I need the mean-free path of a micron, right? Which is not completely insane. Right? And this is also approximately where you would see the wrinkling transition. I think we got to about 3 or something in East West. So you can get a regime.
So the conclusion is there's a window.
Yes.
If you make it clean enough with impurities. Okay.
But this would, of course, the scary part of that one is that it's inevitable.
Yeah,
in there.
exactly.
I completely appreciate that. But so we just happen to be lucky.
You have a question? Yeah. So, probably still a question about the polarization. So, each graphene is starting to generate, right?
Yes.
So, do you have any funny selection rules or effects which
No.
are sufficient in the polarized light?
No. Simply because we have ignored spin-off interaction here.
No, but if you share polarized light, it will select more polarization to the
Right, but
well, at least it will be.
to be honest, I haven't parsed it. Yeah.